It's real pleasure to be back here. We were here like 2 years ago for optimization in Julia. Now, lot of people. So I'm going to talk to you about solving optimal control problems with the help of GPUs. And this is a joint work, as you see, with several people, including colleagues from Toulouse and colleagues from Inria, Sofia. So this is about optimal control for ODEs, not PDEs. So essentially, you look at such a problem here, which is a problem on ODEs with typically such a cost, which is a mix of a Meyer term, G of the initial and final values of the state X, okay, plus some Lagrange cost, which involves the state again and the control U. And you have, of course, dynamics, which is defined by some function F. Okay, so it's finite dimensional stuff. F will be valued in some Rn, like the state X, while U is in R some Rm. So essentially our core target are numerical and say geometrical methods, and we essentially focus on direct or indirect solving. When I say indirect, I mean shooting like things. So of course it's very nice to use Julia because Julia is fast, as we all know. It's strongly typed, it's high level. We have AD more or less built in and fast optimizer. So an obvious remark to start with is that such a problem, of course, is very well suited for so-called first discretise and solve strategy, which is the so-called direct approach. Essentially, if you do so, and to do so, you can use the most simple scheme, the so-called Euler scheme, where you can see if you do that you will have one-step scheme for the ODE here, and also for the Lagrange cost. Okay, you have your grid step size Hi, and you will just, in a very simple way, transfer your problem in a so-called NLP1, namely a non-optimization thing that you can solve. The trivial remark here is that, of course, such an approach is very nice for SIMD parallelism, just like in the previous talk of team that we have on kernel abstraction. Since clearly you see that you will, in fact, evaluate a lot of times, okay, the same functions. Namely here, the function f, which is the dynamics, the function g, the function f0, okay? And you will, in fact, evaluate them on a lot of data, on a lot of grid points, in fact. Okay, so you have a time grid, t0, t1, and so on, tn, and you will just run these simple kernels on a lot of data points. So the very simple idea here, okay, is to leverage the fact that we have a very nice optimization solver and modelers. I think in particular to ExaModels, which is very well suited for this kind of solving. In particular, if you use it with MadNLP, okay, you can use both, and then of course we can solve on GPU. So the basic idea here is to use both. And of course, to leverage the fact that we have a very simple domain-specific language here. So just a quick try. If you look at such a problem, a very simple one, okay? So imagine that you have this second-order dynamics here that you want to minimize the L2 norm of the control, right? You will see that in our DSL, it's very simple to write that. Of course, here you can recognize that we have a state in dimension 2, single input control U, second order dynamics that you can write in a very clear way, plus a cost here. Again, this is as close as possible to the math. If you do so, okay, you can just solve, but to do that, of course, we have to build, okay, translation of this into typically the modeler, which is in our case an ExaModel one. So let's dive a bit into the Julia code here. So after all, it's JuliaCon, so let's just have a look. For instance, here, let us scroll down, for instance, to the declaration of the variable. So you see here that you declare, for instance, a state here of dimension 3, okay? This will just result in a declaration of a so-called ExaModel variable, okay, which is of dimension 3, times, of course, the grid size, and so on. Okay, if you want to have a look, for instance, at the constraint, which is typically here, this constraint, okay, which is a constraint at the final time, okay, we vectorize it in a not automated fashion using the macro in Julia, and typically you see that this will be translated into this constraint in ExaModel, okay, where you see that we have vectorized the constraints on the grid size, okay, and on the dimension here. Okay, and the same will be true, of course, for dynamics. Typically here, if you look at the dynamics, which is, for instance, in this case, the one for the first order term of the state x, is that x1 dot is some term which is here just x2. You see again that typically for the trapezoidal scheme, you will just write that you have this quantity here, where you can, of course, recognize the trapeze scheme, okay, that you will again vectorize over the whole grid. And this is, of course, this for loop here, okay, will really go in a fast way through the GPU. This is the role of ExaModel. Okay. So once we have done that, okay, we can really come back. Sorry, we can really come back to the solving. And to solve that is just a simple thing. You just call solve, okay, indicating that you will use the CUDA backend with ExaModel, and you can just make a simple call to MadNLP. So here, what you see is MadNLP, okay, that you will use as an optimization solver. The linear algebra behind is QDSS, okay, and you see a run here on the GPU code just by calling a simple solve, okay. So the solve is pretty fast. And just to finish, let me just point this mini benchmark thing, okay, where we have solved the so-called Godard and quad-rotor problems. So there are just 4 runs here on A100 and H100 and A100 of NVIDIA. And more or less, if you see the performance on the Godard case or in the so-called quad-rotor case, these are simple problems. You will see here that you have a speed up between 2, 5, or 10. More or less, what you see here is that when the grid size is more than 1000, okay, the GPU beats systematically the run on the CPU. So just to wrap up things, okay, it's a way to have a high-level modeling of control thing, okay, fast solving, okay, and of course, if you want to try it, just give it a try. And what you can say, what we can say also is that we have a lot of applications. Typically, I recommend that you go to the talk of David at 5 p.m. on quantum control things. And of course, there are a lot of examples, and I can advise you to have a look. Yes. And what you can do here is, of course, that you can, that you can use some AI thing to generate the DSL. So with that, I thank you, and of course we're open for evaluation.
So thank you, Jean-Baptiste.